In a time-lapse video, it looks like a monster coming alive. For a moment, it sits there innocuously. Then, ripples move across its surface. It bulges outwards, bursting with weird boils. It triples in volume. Its color darkens ominously, and its surface hardens into an alien topography of peaks and craters. Then the kitchen timer dings. Your cookie is ready. What happened inside that oven? Don't let the apron deceive you. Bakers are mad scientists. When you slide the pan into the oven, you're setting off a series of chemical reactions that transform one substance, dough, into another, cookies. When the dough reaches 92 degrees Fahrenheit, the butter inside melts, causing the dough to start spreading out. Butter is an emulsion, or mixture of two substances that don't want to stay together, in this case, water and fat, along with some dairy solids that help hold them together. As the butter melts, its trapped water is released, and as the cookie gets hotter, the water expands into steam. It pushes against the dough from the inside, trying to escape through the cookie walls, like Ridley Scott's chest-bursting alien. Your eggs may have been home to squirming salmonella bacteria. An estimated 142,000 Americans are infected this way each year. Though salmonella can live for weeks outside a living body and even survive freezing, 136 degrees is too hot for them. When your dough reaches that temperature, they die off. You'll live to test your fate with the bite of raw dough you sneak from your next batch. At 144 degrees, changes begin in the proteins, which come mostly from the eggs in your dough. Eggs are composed of dozens of different kinds of proteins, each sensitive to a different temperature. In an egg fresh from the hen, these proteins look like coiled up balls of string. When they're exposed to heat energy, the protein strings unfold and get tangled up with their neighbors. This linked structure makes the runny egg nearly solid, giving substance to squishy dough. Water boils away at 212 degrees, so like mud baking in the sun, your cookie gets dried out and it stiffens. Cracks spread across its surface. The steam that was bubbling inside evaporates, leaving behind airy pockets that make the cookie light and flaky. Helping this along is your leavening agent, sodium bicarbonate, or baking soda. The sodium bicarbonate reacts with acids in the dough to create carbon dioxide gas, which makes airy pockets in your cookie. Now it's nearly ready for a refreshing dunk in a cool glass of milk. One of science's tastiest reactions occurs at 310 degrees. This is the temperature for Maillard reactions. Maillard reactions result when proteins and sugars break down and rearrange themselves, forming ring-like structures, which reflect light in a way that gives foods like Thanksgiving turkey and hamburgers their distinctive, rich brown color. As this reaction occurs, it produces a range of flavor and aroma compounds, which also react with each other, forming even more complex tastes and smells. Caramelization is the last reaction to take place inside your cookie. Caramelization is what happens when sugar molecules break down under high heat, forming the sweet, nutty, and slightly bitter flavor compounds that define, well, caramel. And in fact, if your recipe calls for a 350-degree oven, it'll never happen, since caramelization starts at 356 degrees. If your ideal cookie is barely browned, like a Northeasterner on a beach vacation, you could have set your oven to 310 degrees. If you like your cookies to have a nice tan, crank up the heat. Caramelization continues up to 390 degrees. And here's another trick. You don't need that kitchen timer. Your nose is a sensitive scientific instrument. When you smell the nutty, toasty aromas of the Maillard reaction and caramelization, your cookies are ready. Grab your glass of milk, put your feet up, and reflect that science can be pretty sweet.